first of all, I have posted your homework 5 for you, and I've also posted all of your exam practice materials, so they're ready for you. Should you finish homework 5 before the deadline, you can get started immediately. And I expect to finish homework 5 material today, so that means that the cutoff for the exam material is already going to be a little bit out from when the exam will be held. Should give you a clean 2 weeks to finish homework number 5, study for exam 1, and get a hold of me for any questions should you have any. So that's kind of what we have coming up. I'll let you know exactly when we hit that cutoff point for the homework 5 and exam 1. It'll happen sometime today. And then we'll just keep trucking forward, accumulating some more materials so that you can have a homework number 6 that is due not too far after the exam. Okay, are there any questions before we begin? Okay, so here's, yeah.
This is a sort of vague question. What is your sort of motivation about posting information about how previous class is done? Like, how should we respond to that on an individual level?
Well,
what is the point?
The point of that, as I mentioned on the exam kind of practice sheet, is that when you are taking your practice exams and you're taking them timed and you're trying to simulate conditions of testing, that when you come out and you get a 70%, you shouldn't be too discouraged. You can look and you can see that you were above average or whatever compared to the last cohort, and knowing that I set the average usually at about a B+, you can kind of understand and get a sense beforehand that it doesn't mean you have to get everything right to get a strong score. So, I mean, it's very much, if they gave you your MCAT score and they didn't give you any context of percentiles, then you wouldn't know how to take it, right? So that's essentially what it's for. The other thing, yeah, and then if you notice, the second page is always kind of common mistakes are mentioned and like how many points things are worth. It all kind of gives you a sense of what to expect beforehand, so that you don't have to go into it, and kind of panic that you're not getting everything. It gives you more of a sense of how to strategize for the exam. Any other questions? Okay, so here's what we are working on: static friction. Static friction, the force will vary anywhere from 0 up to a maximum capped off value, and often give you somewhere in between. As far as where you are in between, it's an as-needed situation. So the force of static friction will never exert more force than you need. Its whole goal is to keep the object in place. So it will try to cancel off any force or forces that are trying to move the object. So if you have 17 different forces and all of their collective parallel components to the surface was pushing it forward at 10 newtons and it doesn't budge, well, it's because static friction successfully canceled off that 10 newtons. It does have a maximum boundary because, as you know, if you push hard enough, it won't be able to keep up. And that is where this equation comes in. This equation helps you compute what is the maximum amount that static friction can hold back. So it's good to not become too obsessed with that formula and always think the static friction force is that. It's commonly far less. This is just a way for you to compute how much it could possibly hold back. The only time you should ever use that is if you have some contextual reason from the problem to think that static friction is being taxed to the ultimate limit. Okay. As far as what goes into it, the ingredients are very familiar. The amount of contact force matters, and again, that's measured by the normal force. And there is, once again, a unitless multiplier, a coefficient of friction, which is higher if the surfaces involved are rougher. In fact, you may question, why is it that we would want to rate the surface roughness twice? It seems like we're kind of rating something. A surface is as rough as it is, right? Why do we have to rate the roughness once for when you're sliding across the surface? That's the coefficient of kinetic friction. And then we rate it again when we're talking about them being in place with respect to each other. Well, roughness, of course, we use that very informally. But we're going to find that you actually do have to talk about the roughness, so to speak, in two different contexts. And I'll get a little bit later today into why that is. Okay. But the general gist of the formula is the same. contact force and roughness will determine the ultimate holding limit of static friction. So let me go ahead and do an example using this force. I'm going to have I'm going to revisit the inclined plane. Only this time I'm going to include friction. So we have our inclined plane. The givens are going to be the angle of the incline from the horizontal, the mass on it. I'm going to place it there at rest. And now there's going to be friction. So this is going to be a much more realistic inclined plane than the one we looked at before, which was hypothetically so perfectly smooth it had no friction at all. So I might draw it like this, just to represent there's some roughness to the surface. That's just kind of polite at this point, but from here on forward you should basically assume, unless you're told that it's perfectly frictionless, you should assume that you should do what is the case in the real world, which is that assume there's friction until you're told otherwise. Okay? And to rate that surface roughness, we need to be given the coefficient of static friction. So that tells us something about how rough or not rough is the surface interaction between these two things, the mass on the incline and the incline itself. If I want to be lazy, I'll just say it's the roughness of the incline. So those are my givens. And I'm going to ask two questions about this scenario. First, I want to find an expression for the static frictional force that is always correct. Which means that as long as the object stays at rest on this incline, I want to know what is the general expression for that. My second question is, what is the maximum angle to which I can tilt this thing before it slides? So this represents the steepest angle at which the object will stay in place. If I tilt it any more, it's going to slide. Okay? So let's go ahead and attack this. Problem-solving strategy, 6-step recipe. Step 1, object of interest. Okay, obviously this mass. Step 2, identify the forces that act on it. So we go through. Gravity always acts straight down. Normal force always acts perpendicularly away from the surface. So those two are there even when we're talking about the frictionless inclined plane. But of course, if those are the only two forces, we know that it would slide down. Well, static friction acts opposite that. So if you would slide down, static friction acts parallel to the surface up the incline. So those are your three forces. Okay, that's step 2 out of the way. Step 3, let's choose some axes. So what's the rule for picking axes? If you know the direction of the acceleration, you probably want to set one axis along that axis. But here we don't. We don't have any acceleration at all, and then in which case we just pick axes to minimize breaking stuff into components, which, by the way, leads us to the same decision. We pick x parallel to the surface and y perpendicular, and the reason I've chosen that is not because it accelerates in the x direction, because here it's not going to move. The whole point of it is to hold it in place. But it's because if I choose those axes, 2 out of the 3 forces are already along them, right? Normal force is already plus y, frictional force is already minus x, and only the force of gravity needs the treatment. And luckily it's the same treatment as before. We break that up into components. One into the surface, one along the surface. This is hopefully familiar to you. We did this in class last week. We also, it's also on the homework if you've done that problem already. We learned that this angle is the same angle as the incline. That's something to remember, so you don't have to reinvent the wheel every time. And then our two components, of course, are going to be mg cos theta in the negative y direction and mg sine theta in the plus x direction. And then, along with that step, step 4, which is breaking force in the components, we draw ourselves a nice little free body diagram to kind of catalog what's going on. So there we have it. And whenever I do a free body diagram, I like to make sure that everything is a tug of war along the coordinate axes, x and y, and any diagonal forces get decomposed into their relative axes. Remember, everything inside those parentheses is the size or magnitude, positive number. The pluses and minuses on the outside of the parentheses indicate whether they're positive or negative x or y components. So remember, n without a vector hat is just a size. Force of friction without a vector hat is just a size. G, of course, is just a size, so nothing inside the parentheses will produce an unwanted minus sign. That's good because the signs are already in the front and already taken care of. So let's take stock on what happens here. A good free body diagram, you can pretty much telegraph what's going to come out of the equations. First of all, there's a component of gravity that acts into the incline, and the normal force is going to kill it. That's what protects the solidity of the incline. That's what came out of the equation even with the frictionless incline plane. Because even if there's no friction parallel to the surface, you still can't go into it. So let me just bore you, let me not bore you with the details. Dot, 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 you're going to get the same thing from the y equation that you got with the frictionless inclined plane. There's no difference in the x direction whatsoever. The new force is entirely along the x-axis. It's in the negative x direction. So let's do that. So in the x direction, there used to be an uncontested force. mg sine theta was able to act, and that was the only thing that was going on. So mg sine theta led to our acceleration. So that is the net force, and hence it caused the acceleration you had down the incline. But now, it's got competition, and it turns out if you hold the object, if the object is to be held in place, it's because the frictional force is capable of canceling that off. So we have plus mg sine theta. We have the force of friction in the negative x direction, and if we stay at rest, our acceleration is actually 0. So here's what we have. How much must the static friction force be? mg sine theta. And that is the answer for part A. So that right there tells us what is the job that static friction will always have to do. What is the job it has to do to hold the object in place? It has to counter off mg sine theta, which is trying to get the motion started. So notice that I did not use this. Okay. In fact, I inferred how much the frictional force was by looking at the force that was needed to be canceled off. So mg sine theta is what actually needed to be done. Now, I realize I'm not doing this with numbers, but let's suppose that you compute that. Mg sine theta could come out to be substantially less than this. Okay? Now, if you were to compute this, this would be mu sub s times, and the normal force is mg cos theta. So this is where there's a common source of confusion. Is the force of friction mg sine theta, or is the force of friction mu sub s times mg cosine theta? Those are generally different numbers. So for instance, you might put in and find that this number is 8 newtons, and this number is 10 newtons, right? So which is it? Is it 8 newtons or 10 newtons? It's the 8, right? Because that's what it needs to do. If something's trying to move it with 8 newtons, it doesn't push 10 newtons back. It would go slide uphill. It doesn't make any sense, okay? So its job is to cancel off 8 newtons, and it could hold up to 10 newtons, but it doesn't need to do that, right? Okay? So this is always correct at any angle that it doesn't slide. This is generally less than this quantity, which is, of course, the maximum that it can do. Okay? So at this point, before we jump into part B, it might be instructive to draw some realistic situations. So if we, for instance, had a very, very slight incline, right? We had a very small angle. The force of gravity, if you look at its components, you can see that it's mostly directly into the surface with only a smidge parallel to it. If I were to drop in these components, we have a huge perpendicular component and a very, very slight component trying to move it. So the frictional force needed to cancel that off is not very big. So what you can see is happening there is that most of the force of gravity is acting into the surface. And of course, that needs to be canceled off by the normal force. So we have lots of contact force. And if you have an object being pushed that hard into the surface, then the value of mu sub s times n is very large as well. So the friction is capable of exerting a lot of force, and yet it exerts very little. Okay? So this is the maximum frictional force. But because mg sine theta is so small, the actual frictional force is very small. So you have lots of possible friction force in reserve because the contact force is so high, but the amount of friction you need is very little, which means that the static frictional force says, I got this with one pinky finger. I don't need to exert as much as I possibly can. Okay? So make sure you understand that while frictional force is could be very large here, it doesn't need to be very large here. Okay? So for instance, this would be an example where mg sine theta might be like 1 Newton and mg cosine theta might be 100 newtons or something. Okay? Just making up some numbers. So this is where you could have a lot of frictional force if you needed it, but you need very little. Okay? So let's examine what would happen if we now tilted this to a very large angle. And of course, if you tilt it to a very large angle, then the force of gravity is allotted very differently. If the force of gravity is like this, well, now we find that a lot less of it goes into the surface and a lot more goes along it. So now we have a very, very large amount of force that is trying to move it, and the frictional force has a very large job to do. So that needs to be substantially large. So now, since mg sine theta, the component of gravity pulling along the surface is very large, the force of friction has to be very large to hold it in place. But at the same time, friction's capabilities are weakening because we're getting less contact force, right? Now the normal force is relatively small, so much less contact force and therefore the maximum that friction can exert is getting smaller. So here you can see what it's going to come to a head at some point, right? If what you're asking friction to do is getting harder and harder, and what friction can do is getting smaller and smaller, at some point they will meet, right? At some point what friction needs to do is the most that friction can do, right? So at some point what's going to happen is that the amount of the force of gravity that's parallel to the surface trying to move it is going to be so large that the frictional force that could be exerted is getting smaller and smaller until they're one and the same. And that is what we get to in part B, which is the maximum angle. Okay? So what happens at the maximum angle when theta becomes the maximum angle? The mg sine theta has increased to be equal to mu sub s times mg cosine theta, which has been decreasing. So think of it like this. This number might have increased to 9 newtons, right? The amount of force needed to hold it in place has increased to 9 newtons, and the capabilities on the top end has decreased to 9 newtons. So now, static friction is going to hold on for dear life. The job it's being asked to do is barely what it can do. Okay? So basically what we've done is we've set theta max, by definition, is where friction can be its maximum, and we have this equal sign here, so these are equal. Okay? So let's go ahead and use this as a springboard to solve for the maximum angle. Okay? So the maximum angle is, by definition, where the force that is trying to move it, mg sine theta, is equal to the maximum force that can be exerted by friction, which is mu sub s times n, or mu sub s times, and I'm borrowing it here from the y-axis, mg cosine theta. Remember, the normal force is commonly shared, so you have to be willing to borrow it from one axis and put it on the other. So at theta max, the force trying to move it, which is mg sine theta, is going to be equal. It's going to require every last drop of the maximum force that can be exerted, which is given to us by mu sub s times n. So now we just solve. We cancel off the mg's on both sides. We divide sine by cosine to get tangent. We take the inverse tangent of both sides, and we're good to go. That's my symbolic solution for part B. If you want to know the maximum angle to which something can stay on an incline, you need to take the inverse tangent of the roughness coefficient, the coefficient of static friction. Now you may not have a lot of intuition of the inverse tan, but if you try a bunch of numbers, you will see that as the roughness goes up, the maximum angle goes up. Okay? So if you have something that's very smooth, hopefully it's not surprising that static friction gives out it easier. And if you have something that's very rough, then it can stay to a larger maximum angle. For instance, if you plug in mu sub s is exactly 1, you'll get that the maximum angle is 45 degrees. So for something of that roughness, 45 degrees is the end of the line. So just to kind of demonstrate, I guess I'll go ahead and use this as my incline. So here I have a stapler. At small angles, it easily stays at rest. mg sine theta, trying to get it moving, isn't very big. Static friction easily cancels it without being maxed out. You go to a slightly larger angle. Now mg sine theta is getting bigger, and the frictional force is getting smaller. And at some point, maybe somewhere right around here, mg sine theta trying to move it is exactly equal to the maximum frictional force that needs to hold it back. That's theta max. If I tilt it anymore, it'll slide. Okay. So what's happened there is that mg sine theta continued to grow, and this couldn't keep up with it, right? So that might be instructive to put down at some point. What happens for angles where theta is greater than theta max? Mg sine theta is larger than the maximum that friction